In this lecture segment, we give a brief overview of Unix signals and some associated concepts in process management and shell job control. The ideal model of a program running from start to end does not always hold true. There are a number of events that might interrupt either temporarily or permanently a program's execution before it finishes. Some of these you're already aware of, others you might not be. Now we'll look at how a program may control its response to such interruptive events in a bit, but first let's review a few types of interruptive events. A number of special keystrokes can cause interruptive events. Under Unix and other operating systems, you can end a program by hitting Control-C. A second program-ending keystroke under Unix, more rarely used, is Control-backslash. Both Control-C and Control-backslash generally end a program's execution. The keystroke Control-Z, by contrast, pauses a program, and the program's execution may later be resumed. All of these are examples of interruptive events. Now, runtime errors are also common interruptive events. Seg faults, bus errors, illegal instructions, and so forth. And finally, timer events qualify as interruptive events. Most operating systems, including Unix, let a process request that it be interrupted after some time has elapsed, or be repeatedly interrupted at some regular interval. This lets programs do things like update clocks or advance animations, etc. In Unix, interruptive events of the types just discussed are called signals. Unix recognizes several dozen types of signal and has an integer numbering system to identify each type. For instance, the signal resulting from Control-C has ID number 2. Memorizing the signal numbers is not generally needed, though, since each signal also has a name and a defined constant of that name to represent the signal number. Just include signal.h, as we do up here in our example, and you can use any of these constants, and quite a few more are defined in the documentation. For instance, sigint is the signal for, or the value for a signal Control-C, value 2. Sigquit is the signal for Control-backslash. Sigcont is the signal that one gets when a program is resumed after being paused. Sigstop is the signal that Control-Z, pausing the program, generates. And there are other signals like sigsegv for segmentation fault, or sigpipe for a signal sent when a program writes to a pipe with no readers, which normally causes the program to end as a fault. Sigalarm, an alarm signal. And so it goes. Again, you can look them all up. Now, these all apply to any version of Unix. There are some more specialized signals that appear only in certain Unix versions. When an interruptive event occurs, the kernel is said to send a signal to the process in question. Sending a signal can have several effects depending on the signal and on how the process is configured. In most cases, as we've said, the default result is that the process terminates immediately. In some cases, like for sigstop or sigcont, the process may be paused or may resume running. In almost all cases, however, a process may determine what happens when some signal is sent to it, overruling the default action. It does so via a signal system call, like the 3 calls here on lines 18 through 20. You include signal.h, by the way, as a header to use this call. The signal call takes an int designating a signal and a pointer to a signal handler function to be called when that signal occurs. The operating system will call the signal handler when the signal occurs instead of ending the process. Let's see how this works in our example program. Lines 18 through 20 make 3 signal calls to provide handlers for the signals for Control-C, Control-backslash, and for reawakening the process after a Control-Z. The signal handler functions must take one int and return void, with the one int parameter being the signal number that occurred. This allows one handler to deal with multiple signal types, as nary-die does here, for instance, responding differently based on whether the signal was sigint or sigquit. Now, as you can see from lines 22 through 24, all our example program does is endlessly count upward, announcing each multiple of 100 million that it reaches. However, the sample run includes not just output from the code, signals1.c is its name, but also a full shell command session during which we attempt to kill, pause, etc. the running program. On line 30 of the output, after the program has reached 100 million, we attempt to Control-C it. The result, rather than termination, is a function call to signal handler NariDie, because of the signal call made on line 18. NariDie gives a sassy message, I sneer at your Control-C, and then returns to the main loop. There's no particular point, by the way, in the line 22 through 24 loop where the NariDie is called. The code simply jumps there from whatever machine language instruction it had just completed as of the Control-C, and then it returns to the next machine language instruction after running NariDie. Same happens, by the way, with a slightly different sneer when we try to control / the program. But Control-Z on line 34 does work to pause the program. You can't prevent this pause even with a signal call. And the line 35 that follows is output from the command shell and is part of the shell's job control system. All the various Unix command shell versions offer a means of setting up and tracking multiple running programs, or jobs. At any given time, at most one foreground program gets input from the terminal, and the others are either paused, as ours presently is, or are run in the background, meaning they continue to run as long as they need no input. The shell built-in command jobs, as on line 36, lists all currently running programs, or paused programs, with a job number for each. This job number is distinct from a process ID. It's a shell-provided number. You can tell the shell to resume any paused program in the background via the command bg % and number, where number is the job number, or to resume it in the foreground via the command fg % and number, as we do on line 38 here. Now, resuming a paused program, whether in the background or the foreground, sends it a sig-cont signal. Normally this does nothing, the program just resumes running, but you can intercept it, as we did on line 20. In our case, we just print a message, but a more practical use might be to do display updates or other delayed housekeeping upon awakening. Now, not all signals can be sent via keystrokes, and even those that can be sent that way can also be sent via the command kill. Now, this command should probably have been named send signal, but since most signals result in the process dying unless a handler is set by signal, kill is probably appropriate enough. This kill command sends signal to the process with ID PID, kill-s, and then the signal, and then the process ID. And signal can be either a signal number or a name, as we do here. On line 42 of our sample program, we once again pause the process, and then we list all current processes using the ps command to get our process ID. And this shows that our a.out process has process ID 4008. Then on line 48, we send our process a sigint Control-C signal via kill. And then waking it back up with FG, which by the way wakes the most recently paused process if given no argument, we see that it both gets the sig-cont signal, oh did I fall asleep, and also the sigint signal, I sneer at your Control-C, which was held until we restarted the process. In question 1, do a bit of research on this ps command. and find out how to, say, list all processes on the system, not just those for the current user. Coming back from a pause there. PS-A will do this. The PS command is remarkably useful. It's worth learning about its options. Now, as a final step, we pause the process yet again, and then on line 54, we send it a signal number 9. This is also named sigkill. Now, this signal cannot be given a handler by a signal or any other means. It always results in process termination, and is thus the process killer of last resort for processes that are otherwise ignoring all signals. When we try to foreground the process, we're told, sorry, it's died, and a message comes out saying it was killed. Question 2 here. What do you pass to signal to cause a signal to be ignored completely, not even calling a handler? Look it up in the docs. In answer 2, you pass the constant sigIGN, sigignore, as the handler value. But this doesn't work for signal 9. Now, there's a lot more to signals than this quick intro, but this much should at least give you what you need to handle most signals.